Hello everyone. In this video, I would like to introduce you to new features that we're bringing to DeepMIB in version of Microscopy Image Browser 2.8. DeepMIB is available under Tools, Deep Learning Segmentation, and it can be used to train and apply uh, deep convolutional neural networks for segmentation of microscopy datasets. There are a couple of full tutorials available already. You can find them in the description, but there are fewer significant changes since the initial release, and I would like to explain more over these features now. I started the DeepMIB application from MIB, and here you can already see a few new features. First, we can go here in this drop down at the top in the network panel, and this allows us to select a GPU that we would like to use for segmentation or for training. On the right hand side, there is a question mark button that it is allowing us to see details of the particular CPU or GPU, and depending which option is selected here, you'll get the corresponding information in this window. The next, in the original release, it was required to pre-process images. In this new release, it's not required. It's like an option. And depending on the settings in this preprocess for drop down here at the bottom, you can select whether you want to preprocess images for training, for prediction, for both, or you would like to work without preprocessing. In this case, DeepMIB is compatible with most image formats, and preprocessing won't be done. But you have to split your images into the datasets for training and for validation manually, or you can use the last option, which is split files for training and validation. In this case, DeepMIB will automatically do this transformation for you. The changes that were also done are probably slightly related to the organization of directories. And to guide you through this, I suggest to check this help section here. And in the directories and preprocessing tab, there are different organization schemes explained. So for example, if you use preprocessing mode, in this case, our images needs to be placed, let's say, under the training tab, under the images and labels directories. Then upon pressing a preprocess button, the images will be preprocessed, and the preprocessed images are placed into the directory which we specify here for the results. If we want to use preprocessing, and then if we manually split directories, in this case our train images and train labels should be placed to these corresponding directories, one for images, one for labels, and the images and labels that will be used for validation should be placed under these validation images, validation labels under the training tab. The last option is that when we do it without preprocessing, but we would like to split the things kind of by MIB or DeepMIB. In this case, again, the images and labels should be just placed into these images and labels directories, and then upon splitting with the files will be automatically transferred into the train images, train labels, and validation images, validation labels directories. Again, some additional details about all kinds of directories that are created can be found in this help section. Preprocessing, if you have lots of images, then preprocessing may take lots of time, and in this case, we added also this use parallel processing, and in this case, the images will be preprocessed in parallel. In addition, original release was bound to images that needs to be in this model format. Now we can also use a few other formats as basically PNG and TIFFs. And in this case, if we have images in one of these or labels in one of these formats, we can just specify it here, and that particular format will be used. In addition to this, the model files can also be one single model file per slice, or as in the original release, it can be one single model file that encodes all the labels. Let's see how it works. I have a couple of examples. One example that I would like to use for training of network to detect cells from light microscopy images. And the second example that I'd like to use to train the network to detect cytoplasm and the nuclei of these cells. Let's check the first example. I have the directory which is called one training cells, contains the images that I will use for training. In here I have two directories, one called images, where I have the images, and the labels, where I have the corresponding labels for these images. Let's open the images. So here you can see the actual images, and then if I click on the load button, go to labels, select these files and open them, I can see the corresponding modules. Then here, what we need to do in this, the first preprocessing directory tab, we need to specify the directories. So this is going to be our training directory. Then the second one will be the directory for prediction. And the last directory will be the one where we put results. Okay. So now what we have different options. For example, we would like to we would like to preprocess images only for training. In this case, we can select this training tab. And then let's turn this off because we have just few files. If I press preprocess, then the files that I have in the images and labels will be automatically split into the validation set and the training set. And these files will be copied to the results cells directory. So these folders were created. Let's delete them. Alternatively, what we can do, for example, we can work without the preprocessing. In this case, we can choose this first option, split files for training and validation. And in this case, here in our training directory, we create four other folders which will contain images that will be used for training and validation and their labels. So we can split the files and copy them, or we can split the files and move them. So for now, we'll just use copy because I don't want to move the files from these labels and images directories. So now the files were split, and then in this train images, I have images that will be used for training, and in the validation, I have images that will be used for validation. And then I will just select preprocessing is not required, and then after that, I'll be able to start training. Before, however, I need to make sure that all the settings are correct. I need to say what are the formats for images, like in this particular case, the images are in this mirror mesh format. Then extension for our model. We have, in this case, again, we have a model. And yeah, that's pretty much it. I think basically it may be beneficial to preprocess images for training, but for example, if you want to use this for prediction, you may skip this step because it's basically will take just extra time. Let's now turn this, let's do this preprocessing for training. And then we press preprocess. Then resulting, so let's delete this because we won't use this. So as a result, we have these preprocessed images placed into this results directory. Now let's go to the training tab, and here I will show you the new features that we have for training. The most significant improvement is the addition of 19 different augmentations. The augmentations are allowing to extend the training base of your dataset. For example, currently I have 14 images for training, but using augmentation, I can extend this base significantly using these 19 filters. The augmentations can be turned on, turned off by pressing this augmentation checkbox. And each of the augmentations can be defined using the 2D settings button. So you can see this big list. First item here defines the fraction of images that are going to be augmented. If I have 1 here, it means that all images that are coming to the network will be augmented one or another way. If I have 0.9 here, then it means that 90%, and the 10% of patches that we send to network will stay as they are. Then in each of these augmentation settings, we can have either 2 or 3 numbers. If the settings are as basically can be turned on, turned off, like for example this random reflection over the x-axis, then there are only 2 values. The first value specify whether it's off when it's 0 or when it's on, when in this case it is 1. And then in addition it specifies the percentage of that particular augmentation to be triggered. So now it has 5% chance out of this 90 that the patch will be augmented using this random reflection. Sometimes in some of these settings, you can see that there are 3 values. In this case, the parameter specified not only whether it's turned on, turned off, but it also a range is provided. For example, let's say if we look on this brightness jitter, it means that now we asking the tool randomly change the brightness of our image, and the variation of this random parameter that will be defined is ranging from minus 10% to plus 10%. And again, the probability of this operation is 5%. There are quite many things here, but we will just quickly look at this in greater details. In the options, we have 2 buttons that would allow us reset to the augmentation to default state or disable them. For now, I'll just click this disable. And if I go to the train tab, we can see that the augmentation is disabled. And moreover, their parameters are also, their probabilities are also set to 0. Basically, what we can, for each of these augmentations, we have 2 ways of turning them on and off. We either put their probability to 0, or we can turn it off using this, let's say, first parameter. For example, saying that the probability that it's turned off 0 or 1 on. I think the best way specified is just basically providing the probability, because this way you preserve your range. It is more useful because it's way easier. Now, how we define what would be the range of each of these augmentations. There are default parameters which we can restore by clicking in this reset to the augmentation button. But it's probably the best to adjust these properties on your particular data set. How we can actually see what would be the result. Let's for example look on this example that I have here, where I would like to check what kind of brightness jitter I would like to use. And then what I do here, I put the variation from minus 50% to 50% down and up, and press OK. Then here I have the preview, and this preview would take a patch from the dataset, and then it will it will modify it using the selected augmentations. For now, I have basically nothing selected. Let's put 50% here. So it means that 90% of patches will go to this augmentation step, and half of them will be augmented using this brightness jitter. If I hit preview button, let's see. Oh, I got an error. And yes, so this error actually comes from the fact that my input images have 2 color channels, the blue and green. But in my settings, I forgot to specify that I actually have 2 color channels. This the DeepMIB thinks that I have grayscale images. What I need to do, I need just to change the parameter that reflects the colors to be 2. Let's actually make also the patches slightly bigger. Let's make them 256 by 256 in this particular case. And let's preview them. Okay, so now it shows the 3x3 grid, which can actually be specific. We can change the size of this, for example, to see more. If I put in the settings, not 9, but let's say 16. But for now, the thing is that we're just looking on the empty page. The page has no cells. What we can do, we can change the random seed here for picking up this page from the dataset to a different number or value. Now I put 3. If I hit preview now, then the other patch that I collected is actually includes a cell. And then what table shows me here that if I take this patch with the current settings, The first patch will be augmented using this brightness jitter with the value 0.1, then the second one with the 0.37, and then so on and so forth. And with the probability of 10%, I will get actually the initial patch without any augmentations. What I can also do here, I go back to duty, and for example, I can include another augmentation value. For example, I would like to also include the contrast jitter with the same probability, 50%. And if I start now, preview the patches, then it will show me that the first patch will be augmented using both of these functions. Then the second one will be with the brightness jitter, then another one with the brightness 0.47 and the contrast 0.03. Then again brightness, contrast, so on and so forth. So I can actually see the result of application of both of these augmentation functions. And this way I can basically see what I can expect when I start training. Also, please note that some of these augmentations, for example, the saturation jitter or hue jitter, they won't work with these images because our images have 2 color channels. And for saturation hue jitter, we need to have 3 color channels or RGB images. Okay, so I would go now and reset augmentations so that they're all basically turned on. And maybe what I can do, I can turn off the saturation jitter and the hue jitter because these are not really useful. The rest should probably be fine as it is. And I forgot to mention one single thing here in this preprocessing. So we can use the masking. The masking is the way that we can actually use to exclude some part of the dataset. For example, we can have a mask that highlighting certain areas of the background, and those will be removed. But it's kind of tricky to use those because when you have a patch with a lot of area which will be masked out, you probably won't get very nice scores. So it's a little bit not totally optimal at the moment. It's still possible to use, but some additional testing still needed to make sure that it works in a kind of very useful way. Okay, so let's check some parameters. Well, we have 2 classes now, which is one exterior, one ourselves. Then we put encoder depth to 4. Let's put patches per images 8, mini patch size 4. So these could be like tweaked depending on the GPU. Then in the training, I think we just do this short test. Let's specify also the output network name. I'll put it to this top level here in this project, call it cells, and put this one too, and hit train. So we pre-processed everything, so just hit yes. Let's start. This new version of DeepMIB comes with the updated progress plot, which is coming now. And then this progress plot shows the loss function we would like to minimize and a few other parameters. Now it's actually something is wrong because the time to go is like about 4 hours. Let's wait a little bit. Okay, now it started to do training. It's 2 hours. It still looks quite slow. Oh, yeah, I was showing this the upper part of this network panel, and I forgot to switch from CPU to GPU. So let's actually stop the training now. Yeah, stopping takes a bit of time. Okay, now it's finished. Let's actually switch back to the GPU that I have. Double check that everything is still okay. Okay, one more again feature that I haven't mentioned is this possibility to change activation layer. By default, UNet use a ReLU layer, but sometimes one or another layer may be more beneficial. For example, I was getting in some cases very nice results using this TANH layer. But for now, for this dataset, we're gonna keep this ReLU layer. Okay, let's start training again. New training. Let's see. Hopefully now it will the network will be trained way quicker. So this training progress window has the upper plot, which shows the loss function, and the loss function is the difference between the predicted results and the ground truth that should be there. And we typically want to have this loss function to go to 0 as much as possible. Depending on particular situation, we go fast or not fast. Sometimes it doesn't train at all nicely, and in this case, sometimes it's useful to go and change this random seed to a different value. In this case, network will be initialized using different weights or values or different patches, and then you can get results quicker. The loss function at each individual case is shown in this with the blue line, and the red line shows the validation, when the network is validating itself versus the validation set that we created during preprocessing. This plot shows the accuracy of the training process and validation. Well, you can see that the validation goes and the training goes quite well, but still the loss function is more it's a better way to visualize the training progress. In addition, we have this extra information here, which is like expected time. So we still have to wait a bit, about 5 minutes to finish the training. Here's the total progress, which is calculated depending on the settings they put in by hitting the training button. We can turn on and off the visualization of the input page. This is very nice to really to follow what network sees, and we also can see from time to time the more stronger effect of the augmentation. So, for example, you see that these are the images, and then how they were the corresponding labels and how they were transformed. These parameters of this window can be specified in the options tab. So, for example, we can specify the refresh rate for this plot to make it faster. We can specify how many points it has, and we also can specify this preview. So now the patches that are going to network are previewed, and we previewed about 2% of the network patches. We can preview all of them, but then in this case it will slow down the training, which we try to kind of minimize. So we like to get trained as fast as possible. Okay, so at this moment, let's fast forward to the end of the training. The training is now finished. It took 6 minutes, and it definitely was way quicker than using CPU. Here's the training plot, and let's test it to see how well we can predict the images. Here are the few other actually new things that you can see in the predict tab. The first of all, that we can specify the mini batch size for prediction. The mini batch size is again a number of patches that go at the same time to the network for prediction. And the larger this number, the quicker you potentially can have the results. Unfortunately, it's not linear, but basically increasing this value will allow to do training faster. As a result of the training, we also generate the score files, which are the probability of this kind of files. The probability of a pixel to belong to one or another class. And in this new version, it's possible to select different options for this format. For example, you can turn that off. In this case, you can do the prediction faster. Let's hit predict button. And yeah, whatever it says, it actually what we need to specify here that preprocessing is not required because we haven't done that. And okay, I hit predict. Let's see. All right, so the images were predicted, and then we can hit load images and models to see the result. So these are the images and then the corresponding labels. Okay, maybe turn off the loot. So this is the result of the training of that whatever 12 images for 6 minutes. Then in the evaluate segmentation, there are a few additional options. The evaluate segmentation is allowing us to compare the results of the prediction with the ground truth that may be provided with the images. If I hit the evaluate segmentation, I can specify the parameters that we'd like to use for evaluation. Then we can see that in this particular example, our images have 87% score. But in addition, we can also extract these different parameters. For example, I can hit the save to Excel or CSV file, and then I can calculate occurrence and the dice similarity coefficient. So if I click this, then in the directory with our results, okay, so the file has this dataset metrics or image metrics parameter where it can calculate the, for example, dice coefficient for each image. And this way we can see if this random splitting, we can have some data set that, for example, has very low score. And in this sense, we can potentially have a chance of including that particular data set and image into the training set. One new option is also available in the Options tab, and the trained network can be exported to ONNX format. This feature is yet available only to MATLAB version of MIB. Pressing this button is allowing to specify the network, specify version of the ONNX operator set, and also what to do with the final segmentation layer. Basically, if this custom dice classification layer is used, it needs to be either removed or replaced with another layer. And then this could be done using this operation. One extra feature which is sometimes useful is called transfer learning. And the transfer learning operation is allowing to replace the final layer of the network to adjust it to a different number of classes. As already mentioned, I have also this cytonuclei network, and this network for two materials. If I load these images and load the corresponding labels, you can see that it's to detect cytoplasm and nuclei. Then what is possible is to basically retrain the network that we just trained to the three number of classes. To do that, we need to click, let's first define the directories, the new directories that has these three classes training, then the prediction for the same three classes, and then we create a directory for results. Then let's pre-process this time images for training and prediction, basically the same way as before. Then we go back to the train tab and hit transfer learning. In this case, what we need to do, we need to select the network, the trained network, which would be the network trained for two classes, for cells and exterior. And here we define that the output should have three classes. These are exterior, cytoplasm, and nuclei. And define the name for this. Let's keep it as the same cytonuclei. After this, not a network file, a new network is created here, which is called cytonuclei, but we need to retrain it. I'll tweak a little bit the parameters here to be like 714, and let's train for 50 maybe epochs, and then train. And this, we should not start new training. which is also possible, of course, but this time we'll take this network, which was generated via transfer learning. There are certain class names are missing, so we just need to hit update network button here. So let's do training for a few minutes and check the result. Okay, the training is finished now. Let's see the prediction. So let's click here, go to predict tab, define number of the mini batch size, then generate score files, and then hit the predict. And then load the images in the models. Yeah, so the network was retrained to detect nuclei and cell outlines. Okay, with this I'll finish the introduction of new features, and thank you for your attention.